Math Physics Medicine, MPM, and Viscoplastopology, VPT, differences, similarity, and evolution from geometric topology to viscoplastic energy. Part 2, number 1458, VPT Sharp 021, December 5, 2025 21,30. Gerald C. EclaireMD Foundation. Category, Medical Research Methodology. Preface. This second part of my VPT research methodology paper provides an overview of how VMT and TDA relate to each other, and why they naturally evolved into my unified method called the VPT model, Viscoplastopology. The detailed step-by-step VPT procedure will be introduced separately. The purpose here is to clarify the conceptual and technical connections between viscoplastic energy analysis, VMT, and topological data analysis, TDA. My comments on medicine. My medical research focuses on mortality diseases arising from chronic metabolic disorders, while my MIT advisor, Professor Norman Jones, studied catastrophic structural failures. Both fields involve extreme events, where statistical averages hide the real danger. Traditional biomedical research depends heavily on average-based models, but my work aims to study nonlinear, dynamic, viscoplastic, and irreversible behavior associated with outliers, because outliers are the true drivers of mortality. Medicine has historically been descriptive, and slow to adopt quantitative system models. Education emphasizes memorization, protocol following, and hierarchical decision culture, not mathematical analysis. When these limitations are discussed, some clinicians may feel defensive, even though the goal is simply to introduce more precise, quantitative tools. My statements that everything can be explained numerically reflect my mathematics, physics, and engineering background. They are not meant to dismiss non-quantitative fields. My point is that biomedicine, psychology, economics, and even social sciences can benefit from quantitative tools such as VMT and TDA. These methods do not replace existing strengths, but complement them by adding system-level clarity. Overview of VPT methodology. Although VMT and TDA originate from different academic traditions, they share a deeper logic. VMT, grounded in physics and engineering, studies how stress and strain interact over time and produce irreversible deformation measured by cumulative energy. TDA, grounded in geometric topology, studies how data points form shapes, how those shapes deform, and how connectivity patterns change over time. One measures energy, the other measures geometry, yet both describe nonlinear, dynamic, time-dependent, and path-dependent evolution that does not reset to an original baseline, irreversibility. This makes them suitable for studying chronic disease progression toward mortality and many real-world systems that experience repeated stress inputs. To test the generality of these ideas, I have written about 100 papers across psychology, personality disorders, economics, marketing, business management, social science, political science, zoology, and music cognition. In all these fields, VMT, TDA, or the combined VPT method produced meaningful and deeper insights. Certain liberal arts areas remain challenging, only because they rely more on descriptive narratives than quantitative datasets. VPT methodology, data preparation. In biomedical convention, most biomarkers follow the rule that higher values are worse. In physics and engineering, higher values generally indicate danger. In geometry, a small, compact ball shape represents stability, while a large angular polygon represents instability. My VPT approach follows these same principles. Many real systems have a single output influenced by several strong inputs. To compare inputs fairly, we normalize them by dividing each input by an accepted, healthy or ideal reference level. These become normalized inputs. This calculation process is named as normalization. For VMT, output variables normalization is not required because VMT measures cumulative energy area, rather than point-to-point magnitude. For TDA, normalization of both outputs and inputs improves geometric clarity and makes graphic patterns easier to interpret. In TDA, the output can be normalized, using the lowest, highest, or averaged value. After normalization, values usually fall between 0, x and 1. X or up to 5. X, where 1.0 represents the ideal reference. This scale helps readers see deformation patterns more clearly. After normalization, we may proceed with either VMT or TDA. VMT model. In the VMT model, we start with one output and multiple normalized inputs. The first and the most important step is to calculate the change of the output over time, which I call the strain rate. Multiplying each strain rate by its corresponding normalized input yields the stressor values. Using these stressor values, we draw a stress-strain curve across time. We then compute the area under the curve using calculus. This stress-strain curve area represents the viscoplastic energy, or VMT energy, created by the interactions between the output, strain and multiple stress inputs. These energy values allow us to determine each input, stressor contribution percent and the cumulative VMT energy percent across time. VMT therefore quantifies how repeated input stresses deform the output strain, in an irreversible, path-dependent way. TDA model. In the TDA model, we again begin with one output and multiple normalized inputs. But unlike VMT, which focuses on accumulated energy, TDA focuses on geometric structure and data connectivity. In TDA, we first construct a multi-dimensional data matrix that includes the normalized output and all normalized inputs. We compute the covariance structure and derive eigenvalues and eigenvectors. Eigenvalues represent the amount of geometric variation along each principal direction, while eigenvectors define the orientation of these directions. Once eigenvectors define the axes of deformation, the data points are projected into low-dimensional manifolds, usually 2D or 3D. Beyond 3D, visualization becomes abstract and extremely difficult, so higher dimensions rely on mathematical interpretation instead of graphics. In 2D space, geometric deformation is measured by the enclosed area, formed by the projected data cloud across time. In 3D space, this concept extends to enclosed geometric volume. These area or volume measures quantify the magnitude of system-wide deformation. This parallels VMT energy analysis, but expresses deformation through geometric spread instead of stress-strain integration. After projection, TDA examines shape continuity and point connectivity. Points that stay close across time indicate strong internal linkage among variables. Points that separate or form gaps indicate instability, structural change, or transitions in system behavior. This reveals topological features such as clusters, holes, loops, and branching patterns that statistical averages cannot detect. In summary, TDA measures system deformation by analyzing eigen-defined geometry, 2D area or 3D volume, and evolving connectivity patterns of the data cloud. VPT model, VMT plus TDA. VMT quantifies system burden and cumulative damage using energy areas. TDA quantifies geometric deformation and structural connectivity. Conceptually, both belong to the same family of pattern recognition tools that study nonlinear, time-dependent systems. VMT provides the macro view of cumulative deformation. TDA provides the micro view of geometric and connectivity changes. When combined, VMT and TDA form the VPT model, which offers a unified method to study irreversible deformation in any system that evolves under repeated stress inputs. This includes chronic disorder-induced mortality diseases, cardiovascular decline, kidney damage, strokes, cancer risks, and many non-medical systems I have researched. VPT integrates both energy and geometry to produce a deeper understanding of system evolution across long periods of time. Conclusion: after writing 1,458 medical research papers, including more than 700 VMT analyses and over 50 TDA analyses, I began to see one unified picture forming in my mind. The old boundaries between physics, engineering, and mathematics, or between energy and geometry, gradually disappeared. What remained was one simple idea: these methods are all forms of pattern recognition in the field of data science. Whether I draw a stress-strain curve or a geometric deformation map, I am observing how systems behave under repeated inputs, and how their internal shape changes across time. Once I prepare a dataset with one output and multiple inputs, the overall direction of the result often appears in my intuition with high accuracy. I can usually guesstimate the outcome before starting the full calculations. Only recently did I understand where this intuition comes from. 43 years of college-level education, including 18 years of institutional training, across 6 universities and 8 academic disciplines, and 25 years of independent self-study. Decades of reading, learning, calculating, analyzing, and thinking have trained my mind to recognize patterns at a speed that most people do not see until they finish the entire analysis. Now, at age 79, I understand one truth that I did not fully appreciate earlier in life. Knowledge is the real power, not fame, recognition, authority, or wealth. These things lose all meaning when health fails. My 25 years of self-study in psychology and medicine have taught me that emotional stability and physical health are the true foundations of survival. Without them, nothing else matters. With them, everything becomes possible. This understanding has changed the meaning of my research. I no longer study diseases only to write papers for journals or conferences. I study to stay alive, to understand my own body, and to help others avoid the same suffering. After my recent stroke, research became both my therapy and my guide. It keeps my mind calm and sharp, and it gives purpose to every day. Looking back, I no longer see my academic and professional journey as separate chapters in engineering, physics, mathematics, economics, marketing, business management, psychology, and medicine. They all converged into one continuous path. VMT, TDA, and then combined into VPT, are simply the tools that emerged from this long journey of study. They help me explain what I have always been trying to understand: How systems deform, adapt, recover, and survive, including my own survival from the recent hemorrhagic stroke in the Pons area, a condition known for its extremely high mortality rate. As I continue my work, I no longer chase external validation. The only goals are clarity of concept, understanding of insights, and contribution to society. If even one person can use my insights to improve their health, prevent disease, or gain peace of mind, then my efforts have meaning. In the end, three things matter most: health, knowledge, and curiosity. Everything else fades. Disclaimer: I write this paper not for fame, but to share what I have learned so others can understand their health, prevent disease, and live longer, healthier lives. This content is provided for educational reference only, and does not constitute medical advice. No doctor-patient relationship is created. You may share this summary freely, but it must not be altered, edited, or republished as your own. All intellectual property rights and copyrights for this article and its related materials belong to the author, Gerald C.